Okay, this is the first of 4 short videos looking at solutions to a problem set about exponential and logarithmic equations and modeling. So the first set was some true-false questions. First, when an exponential function, y equals a e to the bt, is graphed on log-log paper, a straight line results. And the answer to that was false. You should use semi-log paper for an exponential function. So an exponential function is really important. This and the next problem about a power function, really, really important where the variable is. So let's look at that. Exponential functions is some multiple of a e to the bt. Here's the dependent variable. Here's the independent. It doesn't have to be a t, but very often it's a time variable. So examples are compound interest, and in fact continuously compounded interest is where the e showed up first for us, and radioactive decay. Now that's where this is negative, but it's still the same kind of function. It's still an exponential model. Okay. Also, simplistic models, usually not very accurate, but simplistic models of population growth, unrestrained population growth. And we were just doing an example where at least some subset of CO2 concentrations in the atmosphere over some time period seem to follow something like that trend. Power functions, quite different and older in terms of most people's experience. Okay. Here's the dependent variable. Here, I'm not using t for the independent variable because it's not nearly as common for this to be a time here. That's the independent variable. So that's just things like y equals x squared, y equals x cubed. Things that get put together often into polynomials. Like that. Okay. But when you have this kind of model, just one single, it's a monomial, is another name for it, a multiple of a power. The variable here is in the exponent, the variable here is in the base, and that's quite different. These guys are not variables. So like y equals 7x to the 3 halves. That would be a power function. Whereas y equals 7 times 3 halves to the t. Notice this doesn't have to be an e. This is just a very standard thing that works well for calculus. And more generally, it's like a times, oh, I don't want to use b for base, just like c to the bt. And we're going to see in other videos that that can be useful. Like 1/2 for radioactive decay, often people use a 1/2 for that. Okay. The main thing is where the variable is. So this stuff works well. These guys become straight lines on semi-log graphing. No, sorry. And these guys become straight lines on log graphing. And if you can go back to the examples that we did discovering that to confirm that. Okay. So that's really, that's most of B. And in particular with the log paper, well, I didn't ask it in the first one, but the slope of the straight line you get is proportional to the rate constant. You can call it b or r or k. It shows up in various letters, but it's this constant here. It's proportional to that constant. It's very nice. Here, the slope of the line is proportional to n. And if you're not guaranteed for this to be true on an arbitrary log paper, but it's nice when the log paper has the same scale horizontally and vertically, and then in fact the slope is exactly equal to the exponent. And when we did this in class, we made sure to actually use that kind of paper. And I think one time for a homework thing, I forgot to have the printout scale correctly, and so that we lost that property. Okay, extrapolating an exponential growth model in the far future. Exponentials grow really fast, especially if you put in big exponents into them, and they're almost never accurate into the far future. D and E were pretty tricky and trying to get people to really read things carefully. This looks an awful lot like the model for exponentially damped harmonic motion. Notice the different letters here, a K in front, a C here. I'm not real consistent about the letters because nobody is, about what you use for the thing in front and what you use as the constant here. Maybe someday I'll try to be religiously consistent. But what you do need to be careful about is things like where you put the parentheses. You take your time, you multiply it by the angular frequency, angular velocity, and then you take the cosine. You don't take cosine of omega, which would be a number, and then just multiply it by t. That's not an oscillating function at all. Similarly here, we've got radioactive decay, yet more choices of letters, initial amount, rate constant is now called K, still totally legal. There is a relationship between the half-life and the K, really important, but it's that they're inversely proportional. The longer half-life, the bigger L gets, the smaller the rate constant goes because it's a speed measurement. Okay, so that's an important difference from what I had here. And then a logistic model is often appropriate when a quantity grows exponentially for small values, but is also limited by a fixed maximum value. And that's absolutely true. And you might want to watch the Intro to Logistic Model video and maybe the 2 short sequels if you want to see some more about that. Okay, so that's it for this video.